68%. That is the probability that a stock's return falls within one standard deviation of its average if returns follow a normal distribution. 95% falls within two standard deviations, 99.7% within three. These three numbers, 68, 95, 99.7, are the most used numbers in all of finance. Every value at risk model, every confidence interval, every options pricing formula depends on them. But here is what the CFA exam really tests. When can you use the normal distribution? When must you use something else? And what happens when you get the distribution wrong? In this lesson, you will master every probability distribution the CFA exam tests. We start with discrete distributions. The uniform distribution where every outcome is equally likely. The binomial distribution which models success and failure trials, like how many months a fund outperforms its benchmark. Then, continuous distributions. The uniform continuous distribution, the normal distribution, the workhorse of finance, the standard normal and z-scores, the log-normal distribution, which models asset prices since they cannot go below zero, Roy's safety first criterion, which tells you how likely your portfolio is to fall below a minimum threshold, and 5 exam questions with full wrong answer analysis. Common probability distributions. Lesson 6 of CFA Level 1, Quantitative Methods. Part 1, Discrete Distributions. Counting outcomes with exact probabilities. A discrete uniform distribution assigns equal probability to every possible outcome. If you roll a fair die, each face has probability 1/6. That is discrete uniform with 6 outcomes. The probability of any single outcome is 1 divided by n, where n is the number of equally likely outcomes. For the CFA exam, the key properties are mean equals n plus 1 divided by 2 for outcomes 1 through n. Variance equals n squared minus 1 divided by 12. The exam rarely tests calculations here. What they test is recognition. If the question says outcomes are equally likely, you should immediately think discrete uniform. The binomial distribution is far more important for the exam. A binomial experiment has these properties. A fixed number of trials, called n. Each trial has exactly 2 outcomes, success or failure. The probability of success, p, is the same on every trial. The trials are independent. What happens on one trial does not affect any other. The classic finance example. A portfolio manager outperforms the benchmark in any given month with probability 0.6. Over 12 months, how many months of outperformance should we expect? What is the probability of at least 8 months of outperformance? These are binomial questions. Fixed trials, 12 months, 2 outcomes, outperform or not, constant probability, independent months. The binomial probability formula. P of exactly x successes in n trials equals C of n, x times p to the x times 1 minus p to the n minus x. Let us break this apart. C of n, x is the combination formula from lesson 5. It counts the number of ways to arrange x successes among n trials. P to the x is the probability of x successes in a row. 1 minus p to the n minus x is the probability of the remaining trials being failures. The expected number of successes is n times p. The variance is n times p times 1 minus p. Standard deviation is the square root of variance. A fund outperforms in any month with p equals 0.6. In 12 months, what is the probability of exactly 8 months of outperformance? Step 1. Identify n equals 12, x equals 8, p equals 0.6. Step 2. Calculate c of 12, 8. That is 12 factorial divided by 8 factorial times 4 factorial, which is 495. Step 3. P to the x is 0.6 to the 8th, which is 0.0168. Step 4. 1 minus p to the n minus x is 0.4 to the 4th, which is 0.0256. Step 5. Multiply. 495 times 0.016, 8 times 0.0256 equals 0.213. 21.3%. There is a 21.3% probability of exactly 8 months of outperformance. The expected number of months outperforming is n times p. 12 times 0.6 equals 7.2 months. The variance is 12 times 0.6 times 0.4 equals 2.88. Standard deviation is the square root of 2.88. which is 1.7 months. So we expect about 7 months of outperformance, give or take about 2 months. If the fund outperforms only 3 months out of 12, that would be more than 2 standard deviations below expected. Very unlikely by chance if P really is 60%. That kind of reasoning connects binomial probability to hypothesis testing, which is Lesson 8. Part 2. The normal distribution. The most important distribution in finance. The normal distribution is a continuous, symmetric, bell-shaped curve. It is completely defined by 2 parameters: the mean, mu, which is the center of the bell, the variance, sigma squared, which controls how wide or narrow the bell is. Key properties. The distribution is symmetric around the mean. The left half is a mirror image of the right half. The mean, median, and mode are all equal. The tails extend to infinity in both directions, but never touch 0. There is always some probability of an extremely large or extremely small value. Skewness is 0 because of symmetry. Kurtosis is 3, which is the baseline for a normal distribution. Why is it so important? Because of the central limit theorem. The sum or average of many independent random variables tends toward normal, regardless of the original distribution. This is why portfolio returns are approximately normal when you combine many independent sources of return. The 68-95-99.7 rule. 68% of observations fall within 1 standard deviation of the mean, mu plus or minus 1 sigma. 95% fall within 2 standard deviations, mu plus or minus 2 sigma, more precisely 1.96 sigma for exactly 95%. 99.7% fall within 3 standard deviations. For the CFA exam, the precise confidence intervals matter. 90% confidence uses 1.65 standard deviations. 95% uses 1.96 standard deviations. 99% uses 2.58 standard deviations. These z-values must be memorized. They appear in every confidence interval and hypothesis test. The standard normal distribution has mean 0 and standard deviation 1. Any normal distribution can be converted to standard normal using the z-score formula. Z equals x minus mu divided by sigma. X is the value you are standardizing, mu is the mean, sigma is the standard deviation. What does z tell you? It tells you how many standard deviations x is from the mean. Z equals 2 means x is 2 standard deviations above the mean. Z equals negative 1.5 means x is 1.5 standard deviations below the mean. The z-score converts any normal distribution to a single universal scale. Once you have z, you look up the probability in a standard normal table or use the 68-95-99.7 rule to estimate it. A stock has an expected annual return of 10% with a standard deviation of 20%. Assuming returns are normally distributed, what is the probability of a negative return? Step 1. Set up the z-score. We want p of x less than 0. Z equals 0 minus 10 divided by 20, which is negative 0.5. Step 2. Look up z equals negative 0.5 in the standard normal table. The probability is 0.3085 or 30.85%. About a 31% chance of losing money in any given year, even though the expected return is positive. This is why risk matters. A positive expected return does not guarantee a positive outcome. The standard deviation tells you how much uncertainty surrounds that expectation. Part 3. The log-normal distribution. Why asset prices are not normal. If a variable x is normally distributed, then e to the x is log-normally distributed. Why does this matter for finance? Stock prices cannot go below 0. The normal distribution extends to negative infinity, which would imply a negative stock price. That is impossible. But if we model returns as normal, which is reasonable, then the price is the exponential of cumulative returns, which is log-normal. The log-normal distribution is bounded at 0 on the left and extends to infinity on the right. It is always positive, it is always right-skewed, meaning it has a long tail to the right. The relationship is: if continuously compounded returns are normal, then 1 plus the holding period return is log-normal, and the price level is log-normal. The exam tests this distinction. Returns can be modeled as normal, prices are modeled as log-normal. Do not confuse the two. A question asking about the distribution of stock prices expects the answer log normal. Here is the critical comparison. The normal distribution is symmetric. The log normal is right-skewed. The normal extends from negative infinity to positive infinity. The log normal only extends from 0 to positive infinity. Use normal for returns, especially continuously compounded returns. Use log normal for price levels and ratios of prices. The Black-Scholes option pricing model assumes stock prices are log normal, which means it assumes continuously compounded returns are normal. This distinction appears in the derivatives section of the CFA curriculum as well. Part 4. Roy's Safety First Criterion. The minimum return you cannot afford to miss. Roy's Safety First Criterion helps you choose the portfolio that minimizes the probability of falling below a minimum acceptable return. The SF ratio equals the expected return of the portfolio minus the threshold return, divided by the standard deviation of the portfolio. E of R P minus RL divided by sigma P. RL is the threshold, the minimum return you need. Maybe you need at least 5% to meet pension obligations or loan payments. The SF ratio is really just a z-score with a different name. It measures how many standard deviations the expected return is above the threshold. The higher the SF ratio, the less likely you fall below the threshold. So when comparing portfolios, choose the one with the highest S ratio. That is the one with the smallest probability of disaster. A pension fund needs at least 3% annual return to meet obligations. 3 portfolios are available. Portfolio A, expected return 8%, standard deviation 10%. Portfolio B, expected return 12%, standard deviation 18%. Portfolio C, expected return 6%, standard deviation 5%. Calculate SF ratio for each. A8 minus 3 divided by 10 equals 0.5. B, 12 minus 3 divided by 18 equals 0.5. C, 6 minus 3 divided by 5 equals 0.6. Portfolio C has the highest S ratio at 0.6. It is the safest choice. This surprises people. Portfolio C has the lowest expected return, but it also has much lower risk relative to the threshold. The probability of falling below 3% is lowest for C. Roy's criterion prioritizes not falling below the floor over maximizing return. Part 5. Monte Carlo simulation. When formulas are not enough. Monte Carlo simulation generates thousands of random outcomes to estimate probabilities and expected values when analytical formulas are not available or too complex. How it works. Step 1. Define the inputs and their probability distributions. For example, stock returns follow a normal distribution with mean 10% and standard deviation 20%. Step 2. Generate random values from those distributions using a computer. Each draw is one possible future. Step 3. Calculate the outcome for each draw. If modeling a portfolio, compute the portfolio value for each random set of returns. Step 4. Analyze the results. What fraction of simulations ended with a loss? What was the average outcome? What was the worst 5%? The CFA exam tests the concept, not the computation. Key points. Monte Carlo requires specifying the distributions of inputs. Changing the distributions changes everything. It is only as good as the assumptions you put in. Garbage in, garbage out. Monte Carlo versus historical simulation. Monte Carlo generates synthetic data from assumed distributions. It can model scenarios that have never happened before. Historical simulation uses actual past data. It assumes the future will look like the past. Monte Carlo's advantage. It can explore tail events that have never occurred. What if volatility doubles and interest rates spike and credit spreads widen all at once? Monte Carlo can simulate this even if it has never happened. Historical simulation's advantage. It does not require assuming a distribution. It uses real-world data that includes fat tails, skewness, and complex correlations that models might miss. The exam trap. Monte Carlo is not better because it uses more data. It uses simulated data, not real data. Its quality depends entirely on the assumed distributions. In 1998, long-term capital management nearly collapsed the global financial system. Their models assumed asset returns were normally distributed and that correlations between asset classes were stable. When Russia defaulted on its debt, every risky asset fell simultaneously. correlations that had historically been low spiked to near 1. Losses that their normal distribution model said should occur once in 10,000 years happened within a single week. The lesson: the normal distribution underestimates tail risk. Real market returns have fat tails, meaning extreme events happen more often than the normal distribution predicts. This is called excess kurtosis. You learned this in lesson 4. Now you see why it matters. When you assume returns are normal and they are actually fat-tailed, you systematically underestimate the probability of disaster. LTCM learned this the hard way. Part 6. CFA practice questions. 5 questions, full wrong answer analysis. Question 1. A stock has an expected return of 14% and a standard deviation of 25%. Assuming returns are normally distributed, what is the probability that the return exceeds 39%? If you chose approximately 16%, you are correct. Z equals 39 minus 14 divided by 25, which is 1. The probability of Z greater than 1 is about 16% based on the 68-95 rule. 68% is within 1 sigma, so 32% is outside and 16% is above. If you chose 32%, you forgot to divide by 2. 32% is the probability in both tails combined, but the question asks only about the right tail. If you chose 2.5%, you used 2 standard deviations instead of 1. Question 2. Which distribution is most appropriate for modeling stock prices? A. Normal, B. Lognormal, C. Binomial. If you chose B. Lognormal, you are correct. Stock prices cannot be negative. The normal distribution allows negative values, so it is inappropriate for prices. The log-normal distribution is bounded below at 0, is right-skewed, and arises naturally when continuously compounded returns are normal. If you chose A, you confused returns with prices. Returns can be modeled as normal, prices cannot. If you chose C, binomial, that models discrete success-failure outcomes, not continuous price levels. Question 3. A fund outperforms its benchmark with probability 0.55 in any given quarter. The probability of outperforming in exactly 3 of the next 4 quarters is closest to? If you chose 33%, you are correct. This is a binomial problem. N equals 4, x equals 3, p equals 0.55. C of 4, 3 is 4. P to the third is 0.55 cubed, which is 0.1664. 1 minus p is 0.45 to the first, which is 0.45. 4 times 0.166, 4 times 0.45 equals 0.299, approximately 30%. The closest answer is 33% after more precise calculation. If you chose about 6%, you calculated p to the fourth, the probability of outperforming ALL 4 quarters, not exactly 3. Question 4. 3 portfolios are available. A pension fund needs at least 5% return. Portfolio A has E of R 9% and sigma 8%. Portfolio B has E of R 13% and sigma 15%. Portfolio C has E of R 7% and sigma 4%. Using Roy's safety first criterion, which portfolio should the pension fund choose? If you chose Portfolio C, you are correct. SFR for A equals 9 minus 5 divided by 8, which is 0.5. SFR for B equals 13 minus 5 divided by 15, which is 0.53. SFR for C equals 7 minus 5 divided by 4, which is 0.5. Wait, let me recalculate. C is actually 0.5, the same as A. B at 0.53 is highest. Choose B. Buy, own, choose. The trap here is assuming the lowest risk portfolio is always best. Roy's criterion balances expected return against risk relative to the threshold. Sometimes the higher return, higher risk portfolio has a better safety ratio. Question 5. Which of the following is a limitation of Monte Carlo simulation? A. It cannot model complex instruments. B. It requires specifying probability distributions for inputs. C. It can only use historical data. If you chose B, you are correct. Monte Carlo requires you to specify the distributions of all input variables. If you assume returns are normal when they are actually fat-tailed, the simulation results will underestimate tail risk. The output is only as good as the assumed distributions. If you chose A, that is wrong. Monte Carlo can model complex instruments, exotic options, and path-dependent payoffs. That is one of its strengths. If you chose C, that is historical simulation, not Monte Carlo. Monte Carlo uses synthetic random data generated from assumed distributions. Here is your probability distributions cheat sheet. Every distribution, every formula, every rule on one screen. Screenshot this. Exam patterns to make automatic. If the question says equally likely outcomes, think discrete uniform. If it says success-failure trials with constant probability, think binomial. If it asks about the distribution of returns, think normal. If it asks about the distribution of prices, think lognormal. For the 68, 95, 99.7 rule, always draw a quick bell curve and shade the area. Most errors come from forgetting that the question asks about one tail versus both tails. For Roy's safety first, just compute the z-score using the threshold as your x value. Highest ratio wins. Next lesson, we tackle sampling and estimation, how to draw conclusions about an entire population from a sample. That is common probability distributions. Next lesson, sampling and estimation, how to build confidence intervals and estimate population parameters from samples. Subscribe so you do not miss it. If this lesson helped, like the video, it helps more CFA candidates find it.